Hello everyone, I'm Yoshikazu Kobayashi from Nihon University. Today I'd like to introduce about our latest research topic, new algorithm of acoustic emission tomography that considers change of emission times of AE events during the identification of elastic wave velocity distribution. Today, unfortunately, I'm not able to participate in the conference because my employer didn't give a permission to go abroad because of the situation of COVID-19. But fortunately, the organizers gave this opportunity to me, so I'm very happy that I'm able to introduce my research topic by using this video this time. Before starting the main topic of this presentation, I would like to introduce what is acoustic emission tomography, which is called AET. AT is a technique in which the elastic wave velocity distribution is identified only by using the arrival times of acoustic emission or artificial elastic wave. Actually, AAT is derived on the basis of elastic wave velocity tomography, which is called EWT. In EWT, the elastic wave velocity distribution is identified by using the fast travel times of elastic waves. For calculating the fast travel times, arrival time of the elastic wave at the receivers and the emission time of the elastic waves at the point of excitation is necessary. However, in AET, the velocity distribution is identified only by using the arrival times. The source information is not necessary. This is the advantage of acoustic emission tomography. In this slide, there is a movie that introduces the three-dimensional example of acoustic emission tomography. The left figure shows the reference elastic wave velocity distribution, which was used to calculate the arrival time at the sensor receivers. And right figure shows the how the elastic wave velocity distribution is identified in AT. In time, elastic wave velocity distribution is getting closer to the reference elastic wave velocity distribution. However, you can see these are both of the elastic wave velocity distribution is not identical. We can see that there are some errors on the right figure. So now we are trying to reduce these errors by changing the algorithm of the acoustic emission tomography. Based on the background that I introduced before, the objectives of this study is listed like this. The first objective is confirming the cause of the error of the resultant velocity distributions. We have thought that one of the cause of the error is the resolution of the source localizations. We tried to write the source resolutions to check the influence. However, we couldn't do that because it requires very high computational resources. So in this study, to check the influence, the ray path is approximated as a straight path to reduce the required computational resources. It's slightly different from the real situation, but I think that the tendency of this study is similar to the result with the ray trace. So by performing these calculations, the influence of the resolution is discussed on the basis of the resultant velocity distributions that are obtained with various resolutions. And the second objective is proposing a new algorithm of AET to obtain more accurate elastic wave velocity distributions with less required computational resources. In the conventional AET, the SIRT is used as an identification technique, and emission time of elastic wave is handled as a constant. So by changing these implementations, we try to reduce the required computational resources for checking the effect of the resolution of source location to the error of the resultant elastic wave velocity distribution in AET. A series of numerical investigation is performed in this study. A model which is used in the investigation is shown in this slide. The size of the model is 20 meter in height and 10 meter in width, and the cells are square and that edge is 1 meter. Receivers are installed in every 2 meters on all of the edges, and 100 events are randomly and artificially generated in the model. The arrival time at the receivers are computed by assuming a straight path from the generated source to individual receivers. The elastic velocity distribution is identified by using the computed first travel time as the observed arrival time. And as an identification technique, SIRT, which is conventionally used, adopted as well in this calculation. This slide shows the resultant elastic wave velocity distributions in with different resolution of source locations. There are three figures on this slide. The left figure shows the resultant elastic wave velocity distribution, in which the resolution of the source location is 1 meter. You can see many shadows on the distributions, and accuracy of the distribution is not so high actually. And in the middle figures, the resolution of the source location is 1/8 meters. So resolution of the source locations is 8 times of the to the left figures. You can see the quality of the elastic wave velocity distribution is highly improved, and in the right figure, the resolution of the source location is 1/128 meter. The resolution of the source location is very high in this case, and the accuracy of the resultant elastic wave velocity distribution is very nice as well in this case. So this figure suggests that the error is reduced if the resolution of this source localization is raised. So we could confirm that the resolution of the source location is a very important parameter to improve the resultant elastic wave velocity distribution. This slide shows the result of the numerical investigations. There are so many numerals on the slide, but the very important information is just a normalized error and the number of iterations. As we see in this slide, normalized error is if n equals 1, it means that the resolution of the source location is 1 meter. In this case, normalized error as the convergence is more than 80%. It means that only 20% of the initial error between the observed arrival time and the calculated arrival time is reduced. But if we raised the resolution of the source localization to 1/128 meters, the normalized error as the convergence is 4.23%. It means that more than 95% of the initial error is eliminated. This is very important information. And also, we can see the number of iterations in this slide. If n is 1, 11 iterations is necessary to get convergence. However, if n is raised to 128, the 80 iterations is necessary to get the convergence. So this slide shows this result suggests that appropriate n has to be chosen to get the good result. If n is lower, it's obviously the errors are involved in the resultant velocity distribution. And further, number of iteration is getting higher if n is larger. It means that to get the good result, more computational resource is required because more iterative calculation is necessary. So by improving the algorithm, this situation should be overcome to use this technique in the practical purpose. So in this study, the algorithm of AET is improved. In the conventional method, the emission time is handled as a constant while on the stage of identification. So that's why the observation equation is like this. And this is a simultaneous equations, and in this case, all of the coefficient is positive. So that's why SIRT is used as a identification technique, because it's very simple and it's very robust. However, as I introduced in the previous slide, it takes a long time to get the convergence. In AET, the most expensive procedure is the ray tracing. So if we have to do the iterative procedures many times, the rate race is performed in every iterative procedure. So that's why to reduce the number of to reduce the cost for the rate race, we need to reduce the number of iterations. So that's why in this study, a new technique, a new algorithm is proposed. In the proposed method, firstly, the influence of the elastic wave velocity distributions to the emission time is considered as shown in these figures. So, as a consequence, the observation equation is changed like this. In this case, the coefficient for the simultaneous equation is sometimes negative because this term shows sometimes negative. So, in this case, SIRT is not usable anymore as an identification technique. So, in this technique, in the proposed technique, least square approach is adopted as the identification technique. This slide shows the resultant elastic wave velocity distributions on the basis of the proposed technique. The calculation condition is the same with the previous numerical investigations. As we see, the tendency of the resultant elastic wave velocity distribution doesn't change with the previous numerical investigations. If the source location is the resolution of the source location is lower, we can see much errors, shadows in the resultant velocity distributions. However, if the resolution is raised, quality of the resultant elastic wave velocity distribution is improved, as shown in these figures. So we can see that the accuracy of the resultant velocity distribution is improved if n is raised, as well as SIRT, even on the current the proposed technique. If we say the quality of the resultant velocity distribution is the same with the conventional technique, someone thinks that it's not necessary to use the proposed technique. However, we can see the same statistics with previous numerical investigations. The quality of the normalized error is very similar with the SIRT, so it suggests that the improvement of the algorithm of the AET doesn't contribute to the accuracy itself. Indeed, if the n is 128, the result is normalized error is slightly smaller from the previous examples, but I'm not sure it's caused by the improvement of the algorithm of just a kind of error or not. But the very important thing is the number of iterations. By using the proposed technique, we can confirm that the number of iterations is drastically reduced. And further, if we see the change of the normalized error norm with number of iterations, in case of the proposed technique, the error is drastically reduced in the beginning of the iterative calculations, and after that, it doesn't change so much. So, in case of the proposed technique, there is a possibility that we can quit the iterative calculations, even we hope to get the accurate result. This is the improvement of the proposed technique, and the change of the algorithm would contribute to accelerate the calculation. This is the conclusion that I could get in this study. I don't read all of the conclusions, but I would like to summarize the very important things in the conclusions. In this study, we could confirm that the cause of the error of the resultant elastic wave velocity distribution in AET is the resolution of the source locations. So, for reducing the error, we could confirm that we have to raise the resolution of the source localizations, even we use the rate race technique. And another conclusion is, we changed the algorithm of the AET, especially while the stage of the identification. So, by changing the algorithm, we could accelerate the convergence. So, consequently, we could confirm that we could reduce the required computational resources. It's all over my presentation. Thank you very much for your attention.